chapter is the urinary system, and I'll just be honest, this is my least favorite organ system to teach of all. Here's simply why, is I was never taught it. So at Wayne State, when I took physiology, Dr. Piercy, and he stated this, that his philosophy that was that he was going to cover everything perfectly, but because of that, he might run out of time and not cover everything, which we did not get to the urinary system. So I don't think you can do that anymore because rules changed with accreditation and stuff. So like I have to finish, like there's things I have to cover. And then there's extras, which I also add. And then at UNMC, we didn't cover organ systems in anything other than specific classes, like I had neuroanatomy type classes. And then I also had we studied the basics, like how cells work. Once you know how cells work, you know how tissues work, and then you know how organs work. So at UNMC, we never specifically learned about the urinary system, and I had no friends who did research on it. So that's how I learned a lot of stuff. So my only knowledge on the urinary system comes from your textbook. So if you read the textbook, you will know as much as I do about the urinary system. So it is my least favorite one to teach. If you learn nothing in this next week, I want you to learn there are like 4 steps in creating urine. First one, this is 3 processes, but there's a 4th one too. So, because this is actually to make urine, and then there's one more step after that. So, first thing you do to make urine is you filter your blood. And you make it so you make your plasma go through such a fine filter that you leave everything big behind in the blood, like cells and proteins are all left behind in the blood. The only thing that gives you to your kidneys and to your nephrons are, when you make filtrate, are water and dissolve things like ions, glucose, hormones, drugs, things like that can be filtered out, but only tiny things. Big things, cells and proteins left behind. And then your body does not want to waste things, so you reabsorb all the good things. Like think of like sodium and calcium. How back when we were hunter-gatherers did we even come across sodium or calcium? It was very difficult to do. We had to eat animals basically for that to happen. So we don't want to waste it. So you reabsorb good things like sodium and calcium and sugar. And then you secrete bad things into your filtrate. Bad things are things that just simply should not be in your body in the first place, like drugs and some metabolic byproducts. So there are things that when you secrete them into your filtrate, you secrete them whole. Other things, you actually use your liver to break them down, then it goes back into your blood, and then you filter and you secrete those things out. So things that are secreted out whole, just in my mind, what I always remember are things like ibuprofen, the whole penicillin family, so like amoxicillin and everything related to penicillin, and then all opioids you pee out whole. Meaning, when you take ibuprofen or penicillin and you pee in the toilet and flush it, ultimately, in Columbus, it just gets dumped into the Loup River. And so that is something that we need to be cautious about when we take penicillin, amoxicillin, those things, we do pee it out whole, and it does go into Loup River whole. And it does increase the bacterial resistance for antibiotics in the environment. So that was the 3 things. Now we have urine. So filter your blood to get filtrate, remove all the good things, secrete in bad things into that filtrate, and then you have urine. Now you have one last choice with that urine. Whenever you make urine, it's always the high volume, clear, odorless urine. What your pee should always look like. It should basically look like you're peeing out water. But if you're dehydrated or you have like low blood pressure, what you can do is concentrate that urine into the dark, stinky yellow urine. So that way, you're still getting rid of all the waste products. You're not getting rid of any less waste products, but what you're doing is peeing out less water. You're just concentrating on all the waste products. So that's it. Then we can be done for the week. So I wish. Honestly, I do. I don't like the urinary system. So, okay, so some of the things urinary system can do are regulate blood volume. If you have too much water in your blood, what's your blood pressure going to be? Super high. And so to reduce your blood pressure, you can pee more. If you're dehydrated, what's your blood pressure gonna be? It's gonna be low, and then what you do is that's when you make that concentrated, dark, stinky yellow urine, and you don't pee out as much. And then as long as you're doing what 3 of you are doing now, in front of you, having water, as long as you're drinking water on a regular basis, your blood pressure will go back up. Okay. You can control blood solutes concentration, like of sodium, chloride, potassium, calcium, bicarbonate ions, or no, phosphate ions. All these things, like too much calcium is deadly, too little calcium is deadly. Too much potassium is deadly, too little potassium is deadly. And so you need to maintain homeostasis, and the way we get rid of excess of these ions is to pee them out. And if we don't have enough of them, we make sure to reabsorb them all so we don't waste them by peeing them out. Your urinary system is one of 3 main things that controls your blood's pH. You always pee out a little bit of acid, but you don't pee out a ton of it because your urine shouldn't feel acidic. It shouldn't burn when you pee. But you know what, you secrete a little bit of acid. And then your kidneys, when you are, let's say, when you have low blood pressure, say you're dehydrated, you're not going to make as much filtrate because you don't have enough blood pressure to make you do that. And so what happens is your kidneys can sense that you're making less filtrate. Sorry. I'm getting on a different topic. Sorry. Your kidneys can also sense how much oxygen you have in your blood. If you don't have enough oxygen in your blood, then they can produce a protein called erythropoietin. And erythropoietin makes your bone marrow, your red bone marrow, make more red blood cells. And then with more red blood cells, you can transport more oxygen. And then the final active form of vitamin D is produced by your kidneys. And vitamin D ultimately does everything needed to raise blood calcium levels. You absorb calcium from your food, more calcium from your intestines, you pee less calcium out, and you actually degrade your bones and you remove calcium from your bones to put it in your blood. That's all with vitamin D. Okay, so the anatomy. Your urinary system are your 2 kidneys, your 2 ureters that bring urine from the kidneys to the bladder. You have your bladder and then the urethra, and that's the whole urinary system. It's about is the simplest organ system in our body. Maybe I'd say no. Integumentary system is actually the simplest. This would be second simplest. And then location-wise, your kidneys are retroperitoneal. See, here's the peritoneum inside here. They're outside of it. I don't know why, but they are. And your right kidney is slightly lower than your left kidney because your liver takes up a bunch of space. So they're just, your liver and kidneys can't be in the same place at the same time. So they are, again, retroperitoneal on either side of the vertebral column. They are so they're protected by your vertebrae, and then they're half protected by your ribs. So the top half of your kidneys are protected by your ribs, the bottom half aren't. However, the kidneys sit in a gigantic renal fat pad. This huge fat pad that the kidneys sit in and help protect them. But still, if you're losing a fight and you want to win it, just do a kidney punch or a kidney knee to the kidneys and you'll incapacitate them. It's really painful. And then the actual anatomy. So your kidneys are surrounded by a renal capsule, just a thick connective tissue coating around them. They sit in the perirenal fat, or your fat pad that engulfs and cushions the kidneys. Your kidneys are attached by renal fascia that anchors it to the abdominal wall. And then on the medial side of your kidneys, there's an opening called the hilum. And this opening, a hilum or hilus for singular, allows your blood vessels to go in and out. And then within the hilum, there's an open filled cavity that has your blood vessels, your calyxes that I'll get to in a second, and fat. And that's an open area filled with fat is called the renal sinus. So let's go through all that stuff. So here's your kidneys. See, the right one is ever so just slightly lower than the left one because of the liver. Here's the hilum, where the renal arteries go in, renal veins come out. Here's a perirenal fat pad that protects the kidneys and cushions them. Your ureters taking urine from the bladder to the, from the kidneys to the bladder. So here's a hilum filled with fat and your blood vessels and the things that drain urine away. I'll get to that in a second. Your renal artery going in, renal vein leaving, and then here's a renal capsule, the connective tissue around it. Okay, so inside the kidneys, so underneath the capsule. Now we're going to ignore the capsule for the rest of this chapter. But underneath the capsule, there's two layers. The outer layer, like every organ that has layers, is called the cortex. And the inner layer is the medulla. Okay, the cortex is made up of cortical tissue, and even the cortical tissue extends into the medulla. So this area right here, that's actually made up of cortical tissue, but within the medulla. So let me draw the medulla. I'll circle it. So like here, this is all, that section there, that's all the medulla. And these things right here, that is cortical tissue that extends into the medulla. And these cortical tissues are called renal columns? No, renal. Yeah, renal columns. That's right. I just don't trust myself always. So they're renal columns, and what the renal columns do is they divide your kidney into the renal pyramids or medullary pyramids. Either thing, both names. So each one of these things here, that's a renal pyramid or a medullary pyramid. There. And the columns divide the pyramids from each other. I want to highlight this because a couple of the pictures in the future are going to be highlighted incorrectly by the textbook. So I'm just going to want to point that out. Okay, so cortex is the outer area with cortical tissue that extends into the medulla. Medulla is the inner area that consists of the renal columns and the pyramids. Renal column, pyramid. Renal column, pyramid. The base of the pyramid, like especially look at this one looks like a perfect triangle. See that one? So the base is at the top, and then the apex or the tip has a bunch of little holes called renal papilla. And these papilla are where the urine drips out of, and they drip into these little collecting ducts called calyxes. These are, every renal pyramid has a minor calyx. So there's one, there's one, there's one, there's one. And then the minor calyxes fuse together to form major calyxes. And this one I see two, one here, one here. And then the major calyxes fuse together to form the renal pelvis. And the renal pelvis leads to the ureter. Through the kidneys, urine and the filtrate and then urine moves all due to the blood pressure that I'm going to talk about in a little bit. That's higher in your kidneys than other places. Then I'll go over that mechanism. And then once it gets to the calyxes and the renal pelvis, there we just rely basically on gravity and a little bit of hydrostatic pressure. Like if you had a little like tub of water and you had a hose and you opened up the hose and filled up the tub, that would force the water to keep on coming out. Or you could take the tub and just drain it with gravity. There's two things moving urine through your calyxes and renal pelvis. Gravity, and just the urine just keeps on filling it up, so that pushes the remaining urine, or urine that's already there, out. And then once you get to ureter, then ureters are like your esophagus, where they use peristaltic contractions, where you relax in front of the urine, squeeze behind it, relax in front, squeeze behind, and it moves your urine from your kidney down to your bladder. Okay, so here, this is all cortical tissue. However, really, to be the cortex, we need to lead up these renal columns. So this picture, minus this one, would just lead the cortex, which is above the pyramids. The columns are actually in the medulla, but they're cortical tissue. I'm not going to test you on that, but I don't like to teach you something that's technically not correct. So it just bugs me. Okay, then you have medulla with the medullary pyramids here. And really, the medulla should be this highlighted green plus this highlighted green. And this one should be this minus this. But it's not the big deal. It's just technicalities. Okay. Then you have your renal papilla, the apex of the pyramids, with your where you have little holes, and the urine then drips into the minor calyxes. minor calyxes fuse together to form major calyxes, and they fuse together to form your renal pelvis. And then this area here, around the calyxes, within the hilum, is a renal sinus, and this is just filled with fat, and that's really it, just fat. Okay, so now we're gonna look at the nephron, which is the functional unit of the kidneys. The nephrons are what actually make urine. So, we have, let me think what I want to do first. Okay, types is next. Okay, so first, with a nephron, there is an area called a renal corpuscle. This renal corpuscle has two parts. The inside part is called the glomerulus, which is a capillary bed, and there's nothing really special about the capillary bed. It just has some fenestrae and stuff. They're somewhat open, but not super open. And then you have a Bowman's capsule outside of the glomerulus, and the Bowman's capsule has two layers, and I'll show you those later on when I get closer. But together, the glomerulus and the Bowman's capsule filter your blood to make filtrate, and the filtrate enters the inside of the Bowman's capsule. Then you go from the renal corpuscle to a proximal convoluted tubule. You know what the word convoluted means? It means it's like going all over the place, like how politicians will answer a question without ever answering it. They just talk about other stuff. So that's convoluted. So that means the tubes just meander around, just go in all different directions. And then you have the loop of Henle or nephron loop. The loop of Henle or nephron loop has four parts. You have the descending part and the ascending part, and then each of those has a thick and thin filament, segment. Here's the thick segment of the descending loop, thin segment of the descending loop. This one doesn't show much thin segment, but this one does. More thin segment here, and then thick segment of the ascending. Oh, this is ascending. So thick descending, thin ascending, thick ascending. And then you go to your distal convoluted tubule, and then again, the word convoluted means it's going just all over the place. And then we have after your distal convoluted tubule, you have your collecting duct. And as soon as the filtrate enters your collecting duct, that's when we now have urine. And it's always the high volume, clear, odorless urine that we first produce. And you decide, you pee that out as is, or you concentrate it. And you make it into the dark, stinky yellow urine. So that's the basic parts of a nephron loop and what they are. You have a renal corpuscle that filters your blood, proximal convoluted tubule, loop of Henle, distal convoluted tubule, and in those areas, that's where you have the reabsorption and secretion. Reabsorption of good things like ions and sugars, and then secretion of bad things like drugs. And then the collecting duct is what decides, or not decides, but it allows you to either pee out the high volume, clear, odorless urine, or concentrate it into the dark, stinky yellow urine. There are two types of nephrons. Most of your nephrons, I think it's like 80%, are called juxtamedullary nephrons. No, cortical nephrons. About 80% of them are cortical nephrons, about 20% are juxtamedullary nephrons. So the vast majority of your nephrons are cortical nephrons, so let's go with that first. What they do is with your cortical nephrons, their renal corpuscle is somewhat high up in the cortex. See this one, the juxtamedullary, the renal corpuscle is near the medulla. The cortical renal corpuscle is farther away from the medulla, high up in the cortex. And then in the cortical nephron, the loop of Henle doesn't descend all the way through the medullary pyramid, but the juxtamedullary nephrons do. So, juxtamedullary nephrons, renal corpuscle is low in the cortex, and the nephron loop goes all the way down to the bottom of the pyramid. Cortical nephrons, the renal corpuscle is high up in the cortex, and the loop of Henle does not descend all the way down to the bottom of the medullary pyramid. Both of these produce urine, but the juxtamedullary nephrons have another, even more important role. The role of your juxtamedullary nephrons is to maintain a concentration gradient of saltiness in your medullary pyramid. So it makes your medullary pyramid super salty because that's the only way that we can concentrate your urine. Our urine can only be as salty or concentrated as our medullary pyramid is. Because what does water want to do with salt? Water wants to go to the salt. So if we make our medullary pyramid super salty, we can remove a bunch of water from your urine. And when we do that, it ends up just going right back into your blood supply, into your circulatory system. And then the cortical nephrons are just there to make urine. They do not maintain the saltiness of your medullary pyramid. Okay, now we can look more closely at the renal corpuscle and filtration of your blood. So, your renal corpuscle, again, is this capillary bed called the glomerulus, and then a Bowman's capsule that has two layers. The layer that lines the glomerulus is the visceral layer of the Bowman's capsule, and then the rest of it is the parietal layer of the Bowman's capsule on the outside. Okay, I want to just point out a couple more things before we move on. One important thing is the distal convoluted tubule does come back and interacts with the afferent arteriole. That's one thing. We'll get to that probably on Wednesday on why that's important. And then what I really want to cover right now is this is super important, is that you have a very large diameter afferent arteriole and a really small diameter efferent arteriole. So what's that going to do? So afferent is where the blood comes in, and efferent drains it. So now imagine what that's going to cause. You have a huge supply of blood going in to the capillary bed and a very small supply draining it. So what that ends up doing is creates a lot of extra pressure. Think of like how our power washer works at home. If you have one, you hook it up to your house's hose, and that water just barely comes out and it just falls down. And then what you do is you force it through a tiny, tiny nozzle, and then what happens is the water comes out at super high pressure to the point where you can clean things off stuff. So the only way we're able to actually filter blood is the fact that the afferent arteriole is big and the efferent arteriole is small. And that creates enough extra pressure to not only filter your blood to make filtrate, but also move that filtrate all the way through the nephron until it drips into the minor calyxes. Okay. There's some other words on here that I'm going to get to the next slide. It's better. It's here. Okay, so now what I want to look at is the glomerulus and the visceral layer of the Bowman's capsule. So, the visceral layer of the Bowman's capsule are made up of cells called podocytes. Does anyone know the root word poto, what that means? There's a type of doctor, we have one in town named Faulkner, I think? Or he might have left, I don't know if he's still around, I met him once. A podiatrist? What does a podiatrist study? Feet, yeah. So, see, these are called feet cells because they have little toes, and the toes interdigitate. That means go together like this, like when your fingers all interlock. And then what that causes or creates is little slits called filtration slits. Okay? So then you have, right here you have your capillary, which has some fenestrae. They're not big fenestrae, they're fairly small fenestrae. And then you have the basement membrane of the capillary, and then the filtration slits between the podocytes. Together, those three things make up your filtration membrane. And the filtration is so good that all big things get trapped behind in your blood, like cells and proteins. But what else gets trapped behind? Even bacteria and viruses are too big to move through. So have you ever heard the idea that urine is sterile? When it's made by your kidneys, it is. When urine is first made in your kidneys, it is sterile. And then it enters your bladder and your urethra, and for the vast majority of life, that's also sterile. Because if it's not sterile, what do you have? You have a UTI. It almost only happens in women because of your anatomy. You're more open, and things they can happen down there, like if you wipe incorrectly, if you wipe forward, that's not a good thing. Or if you have like diarrhea or something, like poop can get to your urethra, it's possible. So that's why women tend to have more UTIs. Men almost never get UTIs because of our anatomy. So, and then, so if you don't have a UTI, it's still going to be sterile in your bladder urethra, but what's going to happen as soon as it hits your external urethral sphincter or orifice, which is just in front of your vagina, behind your clitoris, or on the ends of a guy's penis, that area is not sterile. So urine that comes out of your body is no longer sterile, but urine inside your body is. Now here's one thing, is, I come here. So when I worked at UNMC, we had a lot of money. Like, we didn't waste it, but we also, if we needed something, we bought it. And then I went to work at UNL, and UNL does not have as much money for science as UNMC does. UNMC is our main research place in Nebraska. UNL does a little bit. So at UNL, we did not have that much money, so we had to do things cheaper. And so what I did was, at UNMC, I would buy my media pre-made. It would come in a bottle, and it was already sterile. And then we could add things to it as well if we needed to. At UNL, I made it from a powdered form. We filtered our own water, made our own distilled water, added the powder to it, then added other things. But once you get that water and that powder, it's not sterile. Like, we took the distilled water and autoclaved it, but then once you add things to it, that's no longer sterile. So what you do, you have to run it through a sterile filter, which has a filter here and the vacuum to suck it down. And once it goes through this filter is so tiny that not a single virus can make it through it. And so on the bottom, it's perfectly sterile above it, and that's called sterile filtration, which is one of the reasons I always laughed at people who thought masks are ineffective. Masks are not this effective because can you breathe through a filter like this? Absolutely not. Yeah, that's why you have to have that vacuum to pull it through. But guess how effective N95 masks are? It's in the name. We can measure it. We can quantify it. They're 95% effective, which is pretty good. So, except for it would be effective because I have a beard. Like, have any of you ever been fit tested for N95 mask? I was, when I started UNMC, I had to be, and you go into this room and they like have salt in the air, and they like measure the amount of salt that like gets into you. It's weird. So anyways, but N95 masks are highly effective at stopping viruses from infecting you. Okay. Okay, wrong buttons. So again, the fenestrate of the capillary's basement membrane, and the filtration slits all work together to filter the blood, to make filtrate. And all big things like cells, proteins, viruses, bacteria all stay in your blood. Okay, then the filtrate enters the inside of the Bowman's capsule, and then the parietal layer of the Bowman's capsule is a simple squamous endothelium that transitions into a simple cuboidal epithelium of the proximal convolute tubule. Minor detail. And then we're going to come back to this, but here I mentioned earlier see how this distal convolute tubule actually comes back and interacts with the afferent arteriole. This together makes up the juxtaglomerular apparatus, where you have some juxtaglomerular cells that are like smooth muscles that can contract or relax the afferent arteriole. You have these macula densa cells, and you have other cells, and these other cells can like track how much filtrate you're making and how much oxygen is in your filtrate. So how much oxygen is in your blood, and then if you have low oxygen levels, you can release erythropoietin to help make more red blood cells. Okay, I'm just seeing if I skipped anything, and I'm not thinking I have. Okay, so again, the afferent arteriole supplies blood to the glomerulus and it's large. Efferent arteriole drains the glomerulus and it's small. And that size difference creates a lot of back pressure inside the glomerulus, and that pressure is what's used to force the fluids out of your blood and into into your nephron, into your Bowman's capsule. Okay, both these vessels have smooth muscles around them, but the afferent one has even more. So the ejected glomerular cells right here are specialized smooth muscle cells that can constrict or dilate the afferent arteriole. Like, do you remember what I said happened when you like run a marathon? That can happen because your sympathetic nervous system, your blood supply to your kidneys basically cuts off, and these are some of the cells that do it. So you can constrict your afferent arteriole, cut off blood supply to your kidneys, and you stop filtering your blood. You don't cut it off completely, but you reduce it a ton. These cells right here, part of the distal convoluted tubule, are macula densa cells. And then I think they're the ones who measure how much filtrate is moving through your kidneys. And then their extraglomerular mesangial cells, not shown here, are the ones that sense how much oxygen you have in your blood. And then if your oxygen levels are low, you can release a hormone called erythropoietin that makes you produce more erythrocytes, or red blood cells. Okay. And there's also a video that will go over this as well later on. Okay, now we're going to get to the more of the histology of your nephron. So, just like your intestines, the vast majority of things happen right at the beginning. So, the vast majority of things that are going to happen in your nephron are going to happen in the proximal convoluted tubule. So, this is where you're going to have the majority of your reabsorption and the majority of your secretion. So, what type of cell must it be in order to absorb and secrete? Go back first week last semester in lab. In order to absorb and secrete things, you need a lot of cytoplasm. You need a lot of cytoplasm so that the cells don't become saturated as they're absorbing things or secreting things. And then, what else would a cell that's going to absorb a lot of things have on it? A lot of microvilli to increase surface area. So these cells either have to be cuboidal or columnar. In this case, they're cuboidal. And then they have a ton of microvilli to increase the surface area. And then you go from the proximal convoluted tubule to the loop of Henle. The descending loop of the descending part of the loop of Henle is still a simple cuboidal. Sorry, the thick portion of the descending loop is a thick. The thick portion of the descending loop of Henle is made up of simple cuboidal epithelium, and that's why it's thick, because the cells are cuboidal. The thin portion of both the ascending and descending loop of Henle are composed of squamous epithelium, that's why it's thin. The difference between the thick and thin are just the shape of the cells. Because cuboidal cells are thicker, then that's thick, and squamous cells are thinner, so it's thin. And as you go down the loop of Henle, you do have some microvilli, but you get a lot less microvilli in the loop of Henle because the majority of secretion and absorption happens in the proximal convoluted tubule. And the distal convoluted tubule is still a simple cuboidal epithelium, but much less microvilli because you have less absorption and secretion here. And then you have even less microvilli on the collecting duct because you're only really reabsorbing two things in the collecting duct. You're reabsorbing sodium, and you're maybe reabsorbing water, or you're not. It depends on your hormones. Okay. Blood supply to your kidneys, you go from your renal artery that comes directly off your abdominal aorta, and then that divides into segmental arteries. Those divide into interlobar arteries, then to arcuate arteries, and then interlobular arteries, and from there they go to the afferent arterial, glomerulus, efferent arterial, and then there's two sets of capillary beds after the Bowman's capsule. You always have this set of capillary beds called the peritubular capillaries. They're next to your proximal and convoluted tubule. Your peritubular capillaries are responsible for reabsorbing good things into your blood and secreting bad things in your blood. And then your juxtamedullary nephrons have another capillary bed around them called the vasa recta. Vasa recta go around the loop of Henle, and they help maintain the saltiness of your medullary pyramid. Now I'll get to that mechanism later. So then after going through these two capillary beds, we go to your peritubular capillaries into arcuate veins, then interlobar veins, then renal veins. Basically the exact opposite order on those. So interlobular, arcuate, interlobar, and then renal veins. But out of all of this, the most important thing is that the renal afferent arteriole is big and the efferent arteriole is small. Okay. Then here's what I started the class with, and now more of you are here so I can go through it. If you learn nothing from this chapter, I want you to learn that there's 4 things that your blood goes through to make urine. First thing you do is you filter your blood to make filtrate, only taking on water from the plasma and small things, leaving behind cells, proteins, and viruses and bacteria. Then 2, you reabsorb good things like salts and sugars that you don't want to waste by peeing them out. 3, we secrete bad things into there, and the bad things we secrete are things like drugs and metabolic byproducts. And then you now have urine. And that urine is always first produced as a high volume, clear, odorless urine, and then we get a choice. Do you pee that out as is, or do you concentrate it to dark, sticky yellow urine? Those are the 4 steps for your urinary system. 3 of them are listed here. Okay, so let's go over some numbers. I will not test you on numbers in this class, but I want to go through them. And it's all here and here are all the same information. So, okay. So the filtration is movement of fluid from your plasma into the Bowman's capsule. It's fluid plus small things dissolved in there, like ions and glucose. And the reason that the water filters out of your blood into your membrane, into your Bowman's capsule, is due to the pressure difference caused by having a large afferent arteriole and a small efferent arteriole. Okay, now some definitions and numbers. So renal fraction. This is the percent of your cardiac output that goes to your kidneys. And here's just basic, our blood flow in our body. About 20% of your blood flow goes to your brain. About 20% goes to your kidneys. About 20% goes to your spleen. And the 40% goes to the rest of your body. So why do you think we cut off blood supply to your kidneys when your fight or flight response kicks in? Because you can redirect that 20% back to your skeletal muscles and heart and lungs instead of just going to your kidneys to be filtered. So your cardiac output is going to be about 20%, and at rest, what's your cardiac output on average? It's about 5 liters. Because your heart beats around 70 beats per minute, and if you multiply that by our stroke volume, couldn't think of that for a second. Our stroke volume is about 70 mils. 70 times 70 is 4,900. That's about 5,000 milliliters. So 20% of 5,000 is about 1,000. So a little bit more than that, about 1.2 liters of blood flow to your kidneys every single minute at rest. Then, what percent of your blood is actually plasma? Well, plasma is 55% of your blood. So 55% of this 1.2 liters is about 650 milliliters of plasma going into your kidneys every minute. And then the filtration fraction is a percent of your filtrate that leaves your blood and enters your nephron, and that's again about 20%-ish, about 19-20%. And so 20% of 650 is going to be, I don't know, divide by 5, that's going to be 125? Yeah, 125 is 650 divided by 5, right? It's close enough. So anyways, that's how much you make per minute. You multiply that by 60 minutes an hour, 24 hours a day. Your kidneys filter about 180 liters of plasma a day. And how much blood do you have total? About 5 liters. So what does that mean we do with our blood? We don't just filter it once a day, we filter it, let's see. If we do, I don't have a quick calculator on here. I'm just going to use my phone. So 180 divided by 5 means you filter your blood about 36 times a day. That's 1.5 times an hour. So that would be about, divided by 24, that would be about 1.5 times every hour. So that would be once every 45 minutes. So, okay. And then total though, you only pee out about 1 to 2 liters a day total. I pee way more because I drink a lot more water than I'm supposed to, but I do that on purpose. It doesn't cleanse you or anything. That's all BS. Like anything that's ever said to cleanse your body does not do that. The only way to cleanse your body is to do the old school treatments. You know what they used to do way back in the day to treat basically everything? Make you bleed. They take these things that just cut you, you bleed out a bunch. That's really the only way to cleanse you. So like the only way to get rid of all the microplastics that are inside of you is to bleed out a bunch. And so who tends to have more microplastics? Men or women? Men, because we don't bleed as much. You have your menstrual fluid. And that helps clean out your body from all those things that you can't get rid of, which is a good thing. So, drinking more water, anything that cleanses you does not cleanse you at all. Because you always make the high volume clear odorous urine. So if you're peeing a bunch, you're just always peeing that out. So, anyways. And these are just the numbers all worked out for you with math. So filtration membrane prevents big things from entering your filtrate. So blood cells and proteins do not enter your filtrate. That's because of the fenestrate and the podocytes, the filtration membranes and the podocytes. However, tiny amounts of protein might make it into your filtrate, even though it's not supposed to at all. But if any proteins or amino acids do get into your filtrate, you're supposed to reabsorb them all in your proximal convoluted tubule. So normally there should be 0 protein found in your urine. If there is protein in your urine, that means that you have some sort of nephritis. You have some sort of kidney damage, some sort of inflammation or something going wrong in your kidneys. And then the filtration pressure comes from the fact that the afferent arteriole is large, efferent arteriole is small. Okay, so now let's look at the actual numbers for the pressures. Again, I will not test you on these numbers, but we need to go through them. And I only want you to keep these numbers in your head for this week. After this week, I'd appreciate if you remember these on Wednesday. That's it. And then you can forget them. Okay. So, we have your glomerular capillary pressure. This is the blood pressure inside of the glomerulus, and that blood pressure is higher because you have the large afferent arteriole going in and the tiny efferent arteriole draining. So that's going to be higher than normal. So your glomerular capillary pressure is about 50 millimeters of mercury. At the beginning of a normal capillary bed, if you remember, do you remember us talking about this? I'll go back to remind you. It's this one. What are your pressures at a capillary bed? Remember talking about edema? Your pressures are like, your net hydrostatic pressure is 33. So that means that's your blood pressure inside your blood minus the pressure out here. So the hydrostatic pressure in your blood is going to be slightly higher than 33, maybe upper 30s. Even looking back here, in this graph, where do we enter your capillary beds? We start entering your capillary beds here, and what's the pressure? Mid to upper 30s. And it ends at the low mid-teens. So my point is, what's the capillary bed normally? Blood pressure is in the mid-30s. What's the blood pressure in your glomerulus? 50. So that's a pretty significant increase from, like, say 35 to 50. That's a pretty big increase in blood pressure. So your blood pressure in your glomerulus is higher than normal because of that small efferent arteriole draining blood away. Okay, but then you also have capsule hydrostatic pressure. That's the pressure that the fluid already has when it's in your Bowman's capsule. So you're not just having fluid enter into an empty cavity, you're having fluid enter into a fluid-filled cavity. So think about like blowing up a balloon. At first it's kind of hard because it's not stretched out, but once you blow a balloon, what does it get when it gets towards the end? It gets a lot harder to put more air into it because it's already filled with air and the air is trying to come back out. And so same thing with your nephron. Your Bowman's capsule also already has water in it, and so that water in your Bowman's capsule is about 10 millimeters of mercury. And then we have your blood-colloid osmotic pressure. Your colloid osmotic pressure is the pressure that we have in fluids due to all the stuff in there. You remember that slide? I'll just go back to show you. You remember this slide from last semester? Maybe not chemistry, maybe it's cell biology. Next slide. Do you remember that talking about, come on, nope, right here, this one, where we had salt water and distilled water, and the distilled water wanted to go into where the salts were to dilute them out, and that made the column of water rise and creates actual pressure. So, just hoping you remember this. I'm not going to reteach the whole thing. But, so, the fact that your water wants to be around stuff causes you to have a lot more blood-colloid osmotic pressure, because what remains behind your blood is most of the stuff. Most of your cells, all your cells, and most of your proteins remain back in your blood. So your blood has more stuff in it than your filtrate. And so water wants to stay around the stuff. And so that blood-colloid osmotic pressure is about 30 millimeters of mercury, and the colloid osmotic pressure in your filtrate is almost zero, because there's very little stuff in there, just a little bit of sugar and salts, not much. So take that all together, you get 50 of the blood pressure in your glomerulus, minus the hydrostatic pressure in the capsule, which is 10, minus your blood-colloid osmotic pressure, which is about 30, and that nets us about 10 millimeters of mercury, making your filtrate, or making your plasma leave your blood and become your filtrate. And then that pressure also allows your filtrate to move through the entire nephron itself. So your blood cap pressure is 50, minus the hydrostatic pressure out here, minus 10, minus the fact that your water wants to stay around all the stuff like the cells and proteins, the colloid osmotic pressure, taken all together gives us about 10 millimeters of mercury. So what would happen if we dropped your blood colloid osmotic pressure down to your normal blood pressure of like upper 30s? You'd even just say 40. You'd have 40 minus 10 minus 30 would give you 0 pressure. So if you constrict your afferent arteriole or dilate your efferent arteriole, that blood pressure in your glomerulus will drop to the point where you have no urine production at all, no filtrate production at all. And that's what happens the entire time you're running a marathon or doing triathlon, is blood basically stops flowing and being filtered. And even when you're like on a, like if you're on a deserted island, like you guys ever watch Naked and Afraid or any of those survival shows? Like when they go out onto a deserted island where it's hot, they usually pee once. They pee at that, it's that really dark, stinky yellow urine, and for the next like 5 days, they don't pee at all. Not even once, because they're barely getting any water and they're constantly dehydrated, so they just don't make urine at all. Okay, this is just repeating a lot of things I've already said. So the colloid osmotic pressure in the Bowman's capsule is close to 0, not quite 0, but super close to 0, because there's not much stuff in it. Just like a little bit of salts and sugars. All the proteins and cells remain back in the blood. If you have nephritis, like inflammation of the nephrons, then you can actually have proteins make it through the filtration membrane and actually make it into your filtrate. And when that happens, now you have proteins in your filtrate. And then where does water want to be now? It wants to be around the stuff. And so when you have more proteins in your filtrate, you're going to have more water in your urine and you're going to pee out more. We're going to come back to diabetics in a little bit on the same idea for that. And then you have a low resistance to blood flow in the afferent arteriole because it's large diameter, high resistance to blood flow in the efferent arteriole because it's small diameter, and then that causes back pressure in the glomerulus to increase up to 50 millimeters of mercury from 35-ish. And that pressure moves the fluid from your plasma into your Bowman's capsule. And then we can change the diameter and change the constriction of the smooth muscles around both your afferent and efferent arteriole. If you dilate the afferent arteriole, you'll get more urine. If you constrict it, you'll get less. But it's going to opposite with the efferent arteriole. If you dilate the efferent arteriole, you're going to lose that pressure in your Bowman's capsule and you'll make less urine. If you constrict it, you'll actually make more urine. Okay, so we have ways to control a glomerular filtration rate. There's autoregulation. This is where you can control the constriction of the afferent arteriole. So, as your blood pressure increases, there's going to be more blood flowing to the afferent arterioles, and these can respond by constricting. Because if you have too much blood flowing into your kidneys, you're going to filter out too much blood. So they can prevent an increase in renal blood flow. But as we're making more filtrate, and more filtrate is moving past the macula densa cells. Those are these cells right here, macula densa cells, right here, in the distal convoluted tubule. They sense the flow rate of filtrate in the distal convoluted tubule, and then what they do is that as they sense more filtrate, they send signals to the juxtaglomerular apparatus to make the afferent arteriole constrict, to reduce the amount of filtrate you're producing. So if you're producing too much filtrate, you can constrict and you'll make less filtrate. And then I already covered the sympathetic nervous system stimulation, where your sympathetic nervous system, your fight or flight response, makes your arterioles, like your afferent arteriole, constrict to reduce blood flow to your glomerulus, and you produce less urine. And then your filtration drops to just a few milliliters. That should be milliliters, not millimeters per minute. Okay, that was all filtration. That was step 1. Now we're going to step 2, which is reabsorption of good things. So, these things that we want to reabsorb are things that our ancestors had a hard time finding. Our ancestors had a hard time finding things like sugar, sodium, and calcium. Those are very difficult to find in nature. So once we get those in our body, we don't want to waste them. So in order not to waste them, we reabsorb the majority of them. And this reabsorption happens through a bunch of different mechanisms, including simple diffusion, facilitate diffusion, where they have to go through transporter protein, active transport using ATP, symport, and then osmosis is basically, if you reabsorb a bunch of sugars and salts, what's water going to do on its own? It's just going to follow the sugars and salts. So as you reabsorb all the stuff, water follows along with it, because water likes to be around stuff. Okay, so then the stuff that ends up in your interstitial fluid in your proximal convoluted tubule gets reabsorbed, and almost all the water gets reabsorbed. About 99% of the water gets reabsorbed. Because remember, we make about 180 liters of filtrate a day, and we only pee out about 1.2 liters. That's 1% of 180 liters. And all the extra water just returns to your renal veins, and it returns to your circulatory system. Okay, so here are some of the mechanisms on how we reabsorb good things like salts and sugars into our blood from our filtrate. So, what runs everything inside of a cell on a day-to-day or minute-to-minute basis? That is the sodium-potassium exchange pump. That's what runs life. So your sodium-potassium exchange pump is using ATP to pump sodium out and potassium in. So what did that mean? Is there a lot of sodium inside the cell or very little sodium inside the cell? Think any cell. There's very little sodium inside the cell, because if sodium gets inside the cell, we use the sodium-potassium exchange pump to pump it out. So that means you have a lot of sodium in your filtrate, and that sodium wants to go into the cell, mostly due to the concentration gradient. And so what does it do? As we allow sodium to go into the cell, we can symport a bunch of things along with it. As we use the concentration gradient of sodium wanting to go in, we can also pull chloride against its concentration gradient, glucose against its concentration gradient, and even amino acids against the concentration gradient. So we can reabsorb all those things. And then as we reabsorb all the stuff, what does water want to do? It wants to be around the stuff, so reabsorb water. Then once all these sodiums, glucose, and amino acids gets inside the cell, then it undergoes either facilitate diffusion or symport to then move from the cell into your interstitial space, and then through diffusion from interstitial space into your capillaries. And these would be the peritubular capillaries that are around the proximal and distal convoluted tubules. Okay. I hope that makes enough sense. And this is all everything I just said. And then we reabsorb almost all your sodium, all your glucose is reabsorbed, and all your amino acids are reabsorbed in your proximal convoluted tubule, and your filtrate volume reduces by 65% of the 99% that we reabsorb. Okay. Then in your loop of Henle, it's kind of weird. Basically what happens is your medullary pyramid at the top is as salty as the rest of your body, and at the bottom, the apex, it's about 4 times as salty as the rest of your body. And so, basically, since the loop of Henle is going down to that super salty area, there's really nothing we can do to prevent the salts or water from moving in and out. So they just do. So as your loop of Henle, as your filtrate goes down, it gains a bunch of salts because the medullary pyramid is super salty. And then as the loop of Henle goes back up out of the medullary pyramid, all the salts leave right away anyways. So it doesn't really matter. It's basically a moot point. It's a point that doesn't really matter at all. So the salts go in, then the salts go right back out. So really you can ignore the salts. They go in, and the same amount of salts go out. Now the difference is the water. So in the descending loop of Henle, it is permeable to water. Water can exit, and it does. As water exits, it goes directly or into interstitial spaces, then into the vasa recta, and the vasa recta then leaves immediately. And so it basically removes the water from your medullary pyramid. And then your ascending loop of Henle is impermeable to water. Water cannot enter or exit. So this is actually right here is like the main mechanism that is how we make the medullary pyramid salty. Is as water enters the loop of Henle, water leaves your filtrate, and then it goes into your vasa recta, and it leaves the medullary pyramid the right way. So the vasa recta is basically there to suck water out of the medullary pyramid, leaving all the salts behind to make it super salty. And we'll come back to this later on Wednesday. And then in the loop of Henle, we reabsorb about 15% of our water. So 65 plus 15, now we're up to we have already reabsorbed 80% of the water. Yeah. Okay. Your ascending loop of Henle is impermeable to water. Water cannot exit, but your salts that entered can exit right back out. So things like your sodium, potassium, chloride, those things can go from your filtrate into your cells, then right back out of your cells. So the salts go in, then they go right back out in the loop of Henle. Okay. Now we get to your distal convoluted tubule and collecting duct. In these areas, we reabsorb very little. Now we're just reabsorbing a little bit more sodium chloride, a little bit more table salt, and I think some potassium as well. And that's about it. And then, as your filtrate enters your collecting duct, it's now urine. And this urine is as equally as salty as the rest of your body, which the number is 300 milliosmoles per kilogram. That's how salty your cells are, how much stuff you have inside your body. And that is a high volume, clear, odorless urine. And then we get a choice. Do you pee that out as is, or do you concentrate it? But we haven't talked about secretion yet, so we need to cover that first before we get to the fourth one. Okay. Now, another thing, urea is a byproduct of protein metabolism. So when you use proteins for energy, proteins are made up of amino acids, and the amine group, the amine group gets broken down and it gets converted into urea ultimately. And then urea is what gives our urine that urine smell, and it's also where urine gets its name from, is urea and urate ions. And you do pee out about 40 to 60% of the urea that you have, and that's why your urine smells like urine. But then there's also like ammonia in there as well, stuff like that. But urea, you also reabsorb about 40 to 60% of it, and that urea then stays in your medullary pyramid, helping make your medullary pyramid stay super salty. And then we also have other toxic things that are in our blood that we pee out as well, like creatine ion, sulfates, phosphates, nitrates. We reabsorb some of them, but the rest we pee out. Okay, then we get to tubular secretion. So tubular secretion is where we secrete bad things into our filtrate, but we secrete them whole. So, things that, just the ones I always remember are ibuprofen, the penicillin family, and all your opioids are peed out whole. So, I need to tell you this funny story. It's from a really stupid TV show. So there's a really, really cheesy, campy TV show on the Sci-Fi Channel called Z Nation. It's basically, it's making fun of The Walking Dead. It's like, it's The Walking Dead, but they're making fun of it. So it's supposed to be a comedy, is what's supposed to be. There was one episode of this show. I had to watch it by myself because my wife can't handle things like that. So anything I watch, anything horror related, she can't be there. And so I was watching it alone in my office. And there's this episode where there were the people, like the Walking Dead people, came up to this new colony, new settlement. And it turns out this settlement they found was made up of a bunch of juggalos. You know what juggalos are? They're fans who listen to the rap group Insane Clown Posse. So, basically, they're people who listen to really, really bad rap. And they go to these festivals and they're just crazy, a bunch of drugs and alcohol and just crazy time. Anyways, people who like to party a lot. And these juggalos, this was like 200 years into the zombie apocalypse, and since they still wanted their narcotics, what these people did was they all peed into these like big they collected all the urine, and then they put them out into these troughs where they allowed the urine to evaporate, and then what was left behind are the narcotics in the evaporate that were in the urine, and then they took the urine like leftovers and they re-snorted it to get the narcotics and use them again. And I actually laughed out loud alone in my office because I'm thinking that's actually somewhat realistic. It's not realistic because think of all the toxic things you filter out and you try to pee out. So you're going to be restarting all those bad things. But you would actually be able to save your narcotics. So like if you like oxycodone, you can, and you take it, you can pee it out, and all the oxycodone just goes right back in your urine. So if you actually drink your own urine, you'd be re-drinking your narcotics. So. Anyways, and these things are peed out whole. So that means antibiotics, narcotics, ibuprofen all get dumped into Loop River, because that's what our urine does here. So this secretion can be both passive or active, using energy, ATP energy or not. One of the things we do secrete into there is ammonia produced by the nephron cells themselves when they metabolize amino acids. And then you also have things like acid, hydrogen ions, too much potassium if you have that, penicillin, amoxicillin, and all opioids are peed out whole. We can also pee out specific drugs like inulin or PAH, para-aminohippuric acid. These are things that you take, you consume, and then you collect your urine afterwards to see how quickly they make it through your urinary system, to see how well your kidneys are working. If it comes out right away, is that a good thing? Like all of it? No, because then you probably have nephritis. If it doesn't come out at all, then your nephrons are also not filtering urine, and you're probably not making urine anyways. So the way we secrete things, these pictures aren't going to deal with your penicillin or any drugs like that. They're just going to look at the sodium and not sodium, but potassium and hydrogen ions. So, what you do, again, you have your sodium potassium exchange pump running everything to create a concentration gradient. We have very little sodium inside the cell and a lot outside the cell. Then we can do things like antiport. You can antiport sodium in exchange for hydrogen ions that come from that exact same chemical reaction that happens in your red blood cells and your parietal cells that make stomach acid. So you use carbon dioxide and water, combine it with carbonic anhydrase to make carbonic acid. It dissociates into bicarbonate ions and hydrogen ions. We antiport hydrogen ions into our urine to pee it out, and the bicarbonate ions reabsorb into our blood supply. And so they were actually peeing out acid while reabsorbing the base. So together, both those will raise your blood pH. It is cold in here. I did raise it. It was set to 65 when I got in. I put it up to 69. It is getting a little bit warmer. So it is. But that's after a weekend. I don't know who did that. I did not put 65. I would never do that. I do it at home if I lived alone. So, actually, completely off topic. 100% off. This is about heating. My most frugal point in my life ever, probably second most. I lived in an apartment, and it was a ground level apartment. So like my window was like this high, and then went to the ceiling. So it was like partially underground, and then I had apartments on both sides and above me, and they heated the hallway. So basically, I just used the hallway heat and my neighbors to heat my apartment. So basically, I would shut my heat off, like turn it down to like 50, and then I only turn it on when I woke up. I take a shower, and when I was done shower, dry off, and got dressed, I shut my heat off. And this is how much I spent to heat my apartment for an entire year. Above like the $20 base fee is $6. I spent $6 on gas to heat my apartment for a whole year. So then I went from that apartment to a third floor apartment. That's expensive to heat and cool. So get an apartment that's surrounded by others if you want to save money. And it's also nice if your apartment heats the hallway instead of having a door that goes outside. So just things to think about as you move other places. Okay. Back to this. So then we antiport hydrogen out of the cells into the filtrate, and we can do the same thing with potassium. We can antiport sodium in exchange for potassium, and then antiport sodium again in exchange for potassium and pee it out. Okay. So then, just overall review of what's happening. So in order to produce urine, we first filter the urine using your filtration membrane. Then in the proximal convoluted tubule, you reabsorb almost everything. You reabsorb almost all your salts, you reabsorb all the sugars, any amino acid that got in there, and then water follows along passively, just because it follows where the stuff is going. And your volume is reduced by 65%. In the descending, or in the loop of Henle, we have salts go in and out, and you can basically ignore that fact because the salts that go in go right back out. And then only the descending loop of Henle is permeable to water, so about 15% of your water then leaves your filtrate at that point in time. In the ascending loop of Henle, water cannot exit, so water remains, but all the sodium, potassium chloride, and other ions that went in go right back out. And then your urine gets to your distal convoluted tubule and then collecting duct. Once it's in your collecting duct, it's always produced as a high volume, clear, odorless urine, and then you get to choose. Pee that out as is or concentrated. So, when you have a large volume of water being consumed, which is what your generation does all the time, which I think is awesome. One of the few things I like about your generation is that you constantly have water bottles with you, which is very healthy, very good for you to do. So if you're constantly drinking water, your urine should always be clear, odorless, and not yellow. And that's how you should always pee. If your urine is anytime your urine is dark, stinky, and yellow, that means you were dehydrated hours beforehand. And you should have been drinking more water hours ago. So, when drinking water is not available, or when you're like sweating a bunch and you're losing a bunch of water like you're working outside, then your blood pressure drops and your kidneys produce a very small amount of water. And what they do is in order to retain water is you, instead of peeing out all the water, you just reabsorb the water. You can also reabsorb sodium as well if your sodium levels are low. And the more sodium you retain, what else do you also retain when you retain sodium? You retain water. So you're still, even when you're dehydrated and you're peeing only that dark, stinky yellow urine, you're still getting rid of the same amount of waste products as you are when it's clear, odorless urine. Okay, and then the mechanisms that control our urine concentration are the fact that we have a super salty medullary pyramid, and that salty medullary pyramid can suck water out of your collecting duct. And then the countercurrent function of loop of Henle means as the loop for Henle goes down and enters your medullary pyramid, your vasa recta leave, the water goes from the loop of Henle into the vasa recta, and that takes it away from the medullary pyramid immediately. So you're basically constantly sucking water out of your medullary pyramid using your countercurrent flow of your loop of Henle and your vasa recta. And then you can use the hormone, antidiuretic hormone, to determine whether or not your collecting duct is permeable to water or not permeable to water. And we will get to that on Wednesday. Okay, let's actually, we'll just start here on Wednesday. Cool. Good. I did not get your quiz written yet, so I just need your quiz questions right now. That takes time. I just didn't have time because I was grading your lab test. And I have reset up the A&P 1 lab test and stuff, so I didn't have time to write them, so your quiz will be on Wednesday. Okay, and then look, we're almost 43, slide 43, and we're getting